Let's make sure we're recording this. So like I said, we're kind of at the end of section 3.1 over here. We just need to look at this example. So just to kind of refresh your guys' memory, remember we were talking about how to solve some of these more complicated, more complex trigonometric equations. So far, all the examples that we have seen have involved, obviously using algebra, but also some trig identities to try and, simplify our equations. And mainly, we have used the factoring method, when it has come to solving these equations. So you will see a little bit of a difference in example number 5 over here. This guy, as you can see, is a little bit more complicated of an equation. So we have 4 divided by secant square of theta plus 3 cosine theta is equal to 2 times cotangent theta times tangent theta. And again, they're asking us to keep the value of our theta between 0 and 2 pi, not including 2 pi. So the first thing we are going to do is use some of these identities to clean up this equation. Now, remember our goal was to try and see if we can get the equation in one single trig function, right? And if that's not possible, obviously the idea is to try and simplify it as much as we can. So you will see here for 1 over secant squared, and I'm kind of just looking at the fraction here. Of course, we've got that 4 on the top, but for now, I'm kind of letting that 4 be as is. Sorry, so think about it this way. If we look at 1 over secant square theta, well, of course, we know 1 over secant theta is the reciprocal for the cosine function, so that's going to be equal to cosine theta. So of course, if you make it secant square, then that guy becomes cosine square, right? And then since you had that 4 on the numerator, you're just kind of multiplying that 4 into your function, right? So that's where that 4 of cosine squared theta is coming from. Obviously, this guy you're bringing down as it is. But then you will again see we are using the reciprocal identity here again on cotangent, and we're rewriting that as 1 over tangent of theta, right? So obviously, since you have tangent of theta on the denominator and tangent of theta on the numerator, they're canceling each other out. Now, remember, this is a little bit different from what we had seen before, because remember yes, it was at this example that we had said you don't want to go ahead and take the sine theta from one side and divide it on the other side, right? To cancel this out, because this was different. You're taking it from one side of the equation and trying to cancel it from the other side. This one over here with the tangent and cotangent, you're not bringing anything else from one side to the other side, right? Cotangent was being multiplied into tangent, and we know they are reciprocal functions of each other, so they naturally cancel each other out. So just identify that difference between that previous example and this one over here. So the tangent actually cancels out, leaving us behind with just, oops, sorry, I lost my pen. Just with the 2, so you end up with 2 over here. And now you can see, move that 2 to the other side, and we have our quadratic in cosine function. So you've got 4 cosine squared theta plus 3 cosine theta minus 2. And, again, think about this. If you did this as u substitution, you would have 4u squared plus 3u minus 2 equal to 0. And if you really think about this, the guy cannot be factored, because you would be looking at product of 4 times -2, which would be -8. And then how do you split up -8 such that it adds up to +3, that middle term? And you will see there is no calculation which will support that, so cannot be factored here. So there are no factors, which means the only other thing we can do is use the quadratic formula over here, and that's exactly what we have. So you can again use u substitution if you want. They are just using cosine of theta, as the function we're trying to solve for. So you can see our b value, and again, just to remind you guys, our quadratic equation, and I'm just putting this in generic terms, is x equals negative b plus or minus square root of b squared minus 4ac divided by 2a, right? So we are using that. And then, of course, just plug in all of your A, B, and C values in there, right? And you end up getting, sorry, 1 second here, guys. Sorry, my computer is doing its own thing. So here we have negative b plus or minus b squared minus 4ac divided by 2a. Clean that up, and you can see this guy is coming out to be, you know, this, well, real number, but just not a very simple, easy, clean number. So go ahead and plug this into your, you know, calculator, get a decimal approximation, and you can see with the negative root, we are coming up with, let me just kind of clear this up a little. With the negative root, come on. You get negative 1.175. And, you know, again, this is a number smaller than -1. Remember, the range of the cosine function is between -1 and +1. So this number is smaller. So you're going to have no solutions since it's smaller than -1. And then for the positive root, you are, of course, getting positive 0.425, which is, of course, within the range of -1 to +1. So use the inverse cosine function 1.5.152. Another thing you should keep in mind is that these angles are in radian, right? They are not telling us anywhere that this needs to be in degrees, right? So of course, then the assumption is that this is going to be in radian method. Oh, I just froze. Okay, so I don't know what happened again. I'm so sorry. So yeah, basically from the first root, we got no solutions over here, but then the second root does end up giving us two different answers. So like I said, this one was just a little bit different because you did have to use the quadratic formula to simplify it. So if factoring doesn't work, quadratic formula would definitely be the other way to go forward with this. So any questions on this example, guys? Okay. If you do not have any questions on that, then let's move on to section 3.2. Alrighty. So this one, as you can see, is talking about, you know, basically introducing us to new identities. And this one, we are talking about the sum and difference identity. So basically think about this, you know, when we're talking about sum or difference, we're basically saying you are either adding two different angles or you are subtracting two different angles. And right now we're basing this off of the cosine and sine functions. So there's a little bit of, you know, and of course you will be able to bring like a formula sheet kind of thing, you know, on the day of the exam. So you still have that, but it may not be a bad idea to just recognize how each one of these identities is laid out. So you will see with the cosine function, when you have a subtraction or a difference, you actually have a addition symbol when we expand that identity out. And then when you have an addition sign here, you're actually going to have a negative sign over here. And then for the cosine function, it's cosine of both the angles. So cosine of A, cosine of B. And then you're adding or subtracting sine of A and sine of B, right? So you're keeping the cosines together and the sines together for the first two identities. For the sine function, if you have a plus sign here, you actually keep the plus in the expansion. If you have a minus sign here, you keep that minus sign in the expansion. But with the sine functions, you actually go back and forth between sine and cosine. So you can see we start out, whatever that first angle is, you start out with sine of A, cosine of B, and then you switch that order and it becomes cosine of A and sine of, and I know I'm calling it A and B, but it's alpha and beta. And then for the sine with the difference function, so this guy over here, again, same thing, start out with that first angle. So sine of A, cosine of B, and then on the other side, you switch that order and you have cosine of A, sine of B. So, you know, a little bit of a difference between how the cosine sum and difference identity is set up and how the sine sum and difference identity is set up. And even as you guys are working through your homework, guys, I would keep this handy. So if you are already starting to work on a cheat sheet or something for the exam, these would be the identities I would definitely add to them, right? All right, so let's see how we can go ahead and work with these guys here. So this first part is actually showing us why these identities work. So why would, you know, if you're taking the sum or difference of two angles, would actually end up giving us, you know, like for cosine of A minus or alpha minus beta, we're basically saying that's going to be cosine of A, cosine of B, plus sine of A, sine of B. So they're saying basically it can be proven that these identities do in fact work with each other. So looking at this little diagram over here, you can say, you're basically saying, okay, let's consider 2 points on this unit circle. So we've got point P over here, which will actually be, since we're talking about this larger angle here, the coordinates for point P is going to be based on cosine of angle alpha and sine of angle alpha, right? So this will be the coordinate for where the P is. Now for Q, they're basically saying since that is based on angle beta, because Q is just this little angle over here, so the coordinates for point Q will of course then be based on angle beta. So these guys will become cosine of beta and sine of beta, right? So that will be the coordinate for points Q. So basically they are saying if you look at the angle that is formed with P, O, and Q, and let me get my pointer here. So we're talking about this angle here, P, O, and Q. Basically that angle POQ is going to be, you know, the larger angle alpha minus the smaller angle beta. So that's where they're coming out from, you know, POQ as the angle being alpha minus beta. Now they are introducing 2 more points. So they are saying, let's look at angle, point C at on that angle A minus B or alpha minus beta. So that will be this point over here. And since this is based on, you know, alpha minus beta, the coordinates for point C will be cosine of alpha minus beta. And of course, for sine, same angle, right? Alpha minus beta. But what they have done here is they have actually rotated the angle. So just think about if we took the point P and moved it where point C is, and we took the point Q and rotated it where the point D is. So if you take that entire angle and rotate it, that's where you're getting that COD angle coming from. So technically, you know, you're just kind of giving it a little bit of a rotation, which is actually a rotation in terms of angle beta, because that's the distance you would be moving. And so what they're doing is basically instead of leaving that Q, and let me pick a little bit of a different color. So instead of leaving this line Q over here, they're bringing it back to the initial side, right? So they're bringing it on that positive right-hand side of the x-axis or the horizontal axis. So basically we are just taking all of these lines and rotating them, you know, bringing them down. And so that angle of alpha minus beta is going to stay constant. That angle is not going to change. And I'm actually going to remove all of these extra lines in there. Alrighty, so basically what we are saying is rotate that angle. So coordinates for C is going to be cosine of alpha minus beta, sine of alpha minus beta. And then since we brought the point D back onto the original horizontal axis, those coordinates are just going to line with +1 and 0, right? Because obviously we're using a unit circle. So you are at +1 for cosine of 0 and, 0 for sine of 0, because technically this guy would be cosine of 0. This one would be sine of 0, but we know what those values are. So we can just use 1 and 0 as our coordinate plane. So now they are saying, okay, we have all these coordinates that we need. Then they are asking us to use the distance formula to basically find the distance from P to Q. And you can see that's this dotted line over here that we're talking about. So finding the distance between P and Q is going to be the same thing if you were finding the distance between C and D. Like I said, just think of that as the angle being rotated, so that distance will be preserved. The angle measurement will be preserved. None of that is changing. And they do actually talk about that here later on in your textbook, but I kind of like mentioning that ahead of time. So when we're talking about distance formula, remember in generic terms, again, your distance formula is, I'm going to try and squish it somewhere over here. So the distance formula is basically you take the difference between the two x values. So x1 minus x2, and you can reverse the order. You can say x2 minus x1. That doesn't matter. Y1 minus y2, and then we square that. So basically, remember, you're doing this between C and D. They start out by showing us with P and Q first, because that's the distance we are talking about. So the two x values would be cosine of alpha over here for P. And then, of course, for Q, it was cosine of beta, right? So you can see that's where the cosine of alpha minus cosine of beta squared is coming from. And then you do y1 minus y2 for the other guy. So that would, of course, be sine of alpha minus sine of beta, and then squared that entire thing, right? So that's where that guy is coming from. And then we will need to use FOIL to expand these guys. So again, okay, let me save my image over here. And then we can scroll down a little bit. Okay, so remember when you are doing the expansion, I kind of wanted to keep my coordinates here, so I don't want to erase that. So I apologize, guys. I know I'm kind of writing one on top of the other, but I don't know what else to do. So remember, when you are taking A minus B quantity squared, it expands into A squared. It could be plus or minus. So it would be plus or minus here. 2 times AB plus B squared is the expansion. So you get cosine squared here. Then negative, this sign will stay 2 times cosine A cosine B. So that's where this guy's coming. And then the last one was B squared. So that, of course, ends up becoming cosine square of beta. Same thing's going to happen here. You will have sine squared A minus, so keeping that same sign, 2 times sine A sine B, or sine alpha sine beta. And then, of course, sine squared of beta. So again, we're basically using algebra again to try and do these expansions. And then, go ahead and simplify what you can. So combine some of the terms using the Pythagorean identities. And what they're talking about in terms of Pythagorean identities. All right, let me delete that. I'll try and bring it back if I can. You're going to take this guy and replace it with 1 minus sine squared alpha. You are going to take this guy. Same thing here. You're going to take this guy and replace him with 1 minus sine squared beta. The sine squared alpha over here is positive. If you change this guy to 1 minus sine squared, these two cancel out. If we replace cosine squared with 1 minus sine squared beta, well, that negative sine squared beta is going to cancel out with that positive sine squared beta. So think about it. you will be left behind with this guy over here, -2 cosine A cosine B, which is this one right here. You've got -2 sine A sine B, which is this guy here. And then these two add up together, 1 plus 1, and becomes 2. So you see how they cleaned that up, and you came up with this simpler version of the quadratic formula. And this is how far we can go as far as finding the distance between P and Q. Now, for finding the distance between C and D. So finding the distance between C and D, just to remind you guys, and like I said, I know I had to erase that, but the coordinates for C was going to be cosine of alpha minus beta and sine of alpha minus beta. And then remember, D was 1, 0. So those are the points you are going to be using. And same process, and I'm not going to break this one down because I do want to move ahead, but go ahead and expand this. So same idea over here. You're doing A minus B squared, so that expands into A squared, again, plus or minus 2AB plus B squared. So that's where cosine squared is that first part, A squared, minus 2 times AB plus B squared is what this guy is coming out to be. Since this is a 0, basically that goes away because your second coordinate was 0, and you're just squaring sine of alpha minus beta. So this one is much more simpler because we did actually have actual numbers over here for the second point. And remember, this was D, this was for point C. So clean this up again, and you're basically coming up with -2 cosine of alpha minus beta. So this guy stays. And again, I can rewrite this cosine as 1 minus sine squared alpha minus beta. So that negative sine squared will cancel out with the positive sine squared, leaving us behind with this one over here. And then you also had a 1 there. So 1 plus 1 again ends up giving us 2, right? Now, like I said, you are literally just rotating that POQ angle and making it the COD angle in our graph over here. So the distances P to Q and the distance C to D stays the same, and that's why they are taking both sides and setting them equal to each other. So again, let me go ahead, clear this out. So we are literally taking this simplified answer that we got for the distance from P to Q, and we are taking this simplified answer, which represents the distance from C to D, setting it equal to each other. So basically, we can go ahead and take a square on both sides. Square and square root cancel each other out. Whatever you are left with, simplify that, clean it up. So basically, the 2's will cancel each other out. Let's see, yeah, you can actually factor out this -2 and this -2, and it will cancel out with this -2 over here. So just imagine if I took the entire equation and divided it by -2 on each side, right? So this guy would cancel out on the right, and then these guys would cancel out on the left. So now what are we left behind with? Our identity. So you are left behind with cosine of alpha plus beta. Cosine of alpha times cosine of beta. You are left behind with sine of alpha times sine of beta on the one side. And of course, on the other side, we are left behind with cosine of alpha minus beta. So it's a long process. You guys do not have to replicate this, but you do need to understand where the identity is coming from. It's not just something that, was randomly created. It's basically a full mathematical process. And this is how we came up with this identity. And this is pretty much going to be similar to, if you were to break down how the other identities were created. So all 4 of these are basically based off of this same type of explanation. So you can show that the left-hand side is going to be equal to the right-hand side, okay? All right, guys, so like I said, you do not have to replicate this. You just need to understand where those identities are coming from. So this guy is actually very simply asking us to write the cosine of alpha plus beta as cosine of alpha minus negative beta, right? So they're just having us rewrite that plus as two negatives. And then they are saying, show that the sum of angles identity for cosine follows from the difference of angles identity that we have just proven above here. So let's start by rewriting, and you know what? Let me open up our draw board over here. Sorry, I do need to go ahead and delete all of these extra pages here. All right, so let's take a look at how we can rewrite that cosine of alpha plus beta identity. So let's make this guy a little bit bigger. Okay, so this was the try it now. And we are doing the first one. So cosine of alpha plus beta, you are rewriting this as cosine of alpha, oops, sorry, minus and then negative. Okay, so remember what the original identity was. Let's come back over here. So the original identity for cosine of alpha plus beta is cosine of alpha, cosine of beta, minus, remember you switch signs for the cosine function, so minus sine of alpha, sine of beta. So how would we translate that over here for this guy? So of course you want to start out by writing that first part. Remember, it's cosine of alpha. Actually, no, I'm sorry. This was originally the positive, but we're rewriting it as a negative. So you are actually looking at this identity here since we're writing it as alpha minus negative beta, right? So you would be using this guy. So the only difference is instead of a minus sign, you would actually be using a plus sign over here. So this is the identity we will be using to break it down. All right, let's come back here. So cosine of alpha, and this will then become cosine of, but we would be using negative beta, right? Since my second variable or second angle is negative. So since this guy is a negative sign, remember this guy has to be positive in here. So now you will be doing sine of alpha times sine of negative beta. So what happens when we use negative angles inside a sine and cosine function? How would you clean up? Because, you know, of course, cosine of alpha will stay the same. So cosine of alpha will stay the same. But what happens with cosine of negative beta? What happens when we use a negative angle inside of a cosine function? Do you guys remember that? Because remember, this is where we had talked about those negative angle identities or the odd or even functions. So how cosine behaves and how sine behaves when they're odd or even. Nobody? We don't know what we're going to come up with. Yeah, thank you, Jeff. So yeah, the cosine function absorbs the negative sign, right? So the cosine will actually end up becoming positive. So you will end up with cosine as positive beta, keeping that plus sign for now. Same thing, right? Sine of alpha will stay the same. What happens with sine of negative beta? What happens with the negative sign inside of a sine function? Does the sine function also absorb the negative, or the negative stays? It stays, yeah, Marquise, very nice. So this will actually end up becoming negative sine of beta, which means that you are basically taking positive over here and a negative sign over here. So positive times negative will, of course, end up becoming negative. And you can see this is where we are able to show that this, in fact, is the identity for the sum of two angles. So cosine, come on, buddy. And then this guy becomes negative, and that's sine of alpha, sine of beta. Okay, which is what we had for the second one, right? Because then this guy ends up becoming negative. And basically that's what we have just proven by writing it out as the first identity using its rules, and then proving that you do in fact get the second identity on that. Did anybody have questions on this first try it now? Okay. So let's look at how we can basically use these rules over here. Okay, something just came on chat. So remember the negative angle identity for the sine function is, where did my pen go? Hold on a second here, Phoenix. So remember the negative angle identity for sine function is that if you have a negative angle, it basically makes the entire sine function a negative value. So that's what we're basically saying. If the angle is negative, you can bring that negative sign outside and the entire sine function becomes negative. So that's what we've done, is we've taken this negative sign and brought it outside over here. And then because you had a positive sign here, positive times negative multiplies together and ends up making this sign in the middle be a negative sign. Got it? Okay, wonderful. Thank you. All right. So let's go ahead, clear this out. Alrighty, wonderful. So as I was saying, let's take a look at how can we use these identities to help us actually simplify functions, right? Which is what we're trying to do here. So the idea is then, we have something like, they're asking us to find the exact value. And guys, when they're saying exact value, they of course mean not a decimal approximation, right? For angle 75 degrees. Now, if you go to your unit circle, you will obviously see we do not list out the 75-degree angle. We have, 0, 30, 45, 60, 90 in that first quadrant, which is where 75 would be. But obviously we have nothing listed for angle 75. So this is where we can use that sum or difference identity and come up with an exact value. So you will see we are rewriting 75 as 30 plus 45. And the reason you are using 30 and 45 specifically is because those are the two angles that are available to us in the unit circle, right? So we've got 30, we've got 45, so we can actually use their coordinates to figure out what the value would be. So you take 75, break it down into 30 plus 45. So of course, since this is a plus sign, remember the identity will have a negative sign. So you will do cosine of 30, cosine of 45, minus sine of 30, sine of 45. Now cosine of 30, and again, let's go to the unit circle very quickly. So cosine of 30 is going to have the coordinates square root of 3 halves and 1/2, and sorry, not cosine, but both cosine and sine. And for 45, same thing, cosine will be square root of 2 over 2, sine will be square root of 2 over 2. So those are the values we are going to use. So again, cosine of 30 is where the square root of 3 over 2 is coming from. Cosine of 45 is where square root of 2 over 2 is coming from, and then minus sign from our function here. Then sine of 30 is 1/2. Sine of 45 is square root of 2 over 2. So clean that up. You can see when we multiply square root of 3 times 2, we will get square root of 6. When we multiply 1 times square root of 2, of course, we get just square root of 2. There's a minus sign in the middle, so that's where this minus is coming from. On the denominator, 2 times 2 will, of course, add up to give you 4. So that's basically how you are simplifying and coming up with the exact answer for what will cosine of 75 be. Now, of course, you can throw this into your calculator and you'll get some decimal approximation for that, but, that was not the goal of the question. Now, this was with degrees. We can obviously do this with radians also, and that's actually what the try it now is asking us to do, is look at the exact value of sine of pi over 12. So let's do that. Let me erase this out. Okay. All right, so exact value of sine of pi over 12. Now, again, if you look at the unit circle, you will see that we do not have a pi over 12 over here, right? Our denominators are 2, 3, 4, 6, and then, of course, this guy has a denominator of 1. So we don't really have pi of 12 over there. So, of course, that means we will need to break down and write this as, either the sum or the difference of two different angles. Now, this one may take a little bit of playing around because, obviously it's not as easy as just looking at the degree measurements and saying, oh, I can break down 75 into, 30 and 45. So the one thing you have to do is look at that denominator 12. Now, 12 can be broken down into 6 times 2, or it can be broken down into 3 times 4. Now, of course, you can do 1 times 12, but that's not going to help us. The reason why I'm using 6 and 2 or 3 and 4 is because that's what the denominators in these angle measurements are, right? In the unit circle, and that's what we want to use. So if you did 6 and 2 as your denominators, I'm sorry, that should be either a plus or a minus sign. You have to make sure if you add them together or if you subtract the two fractions together, your numerator should only add up to 1, right? Because that's what you have, 1 pi over 12 over here. So, if you just did pi and pi over here, what would we end up with? Because, you would have to do a common denominator, which means multiply this guy by 2 over here. And then we would have to multiply this guy by 6 over here. So that would end up giving us 2 pi plus 6 pi, which is 8 pi over 12. And that's not going to reduce down to pi over 12. So that's not going to work. If you did pi over 6 minus pi over 2, same thing, you would multiply this side by 2. You would multiply this side by 6, and that would end up giving us negative 4 pi over 12. So, of course, that still does not give us pi over 12 that we were looking for. So that's actually telling us 6 and 2 are not going to be our denominators. So you want to try basically the same thing with 3 and 4 now. There we go. All right, so if you did 3 and 4 as your denominators, sorry, I didn't mean to use that writing pen. There we go. So if we use 3 and 4, as our denominators. Again, we'll start with pi, and pi you can do plus or minus. So if we did plus, I don't think that's going to work out either, right? Because we multiplied this by 3, multiplied the other one by 4, and you end up with 4 pi plus 3 pi, which will be 7 pi. So the addition is not going to work. What happens if we change that to subtraction? And if you change that to subtraction, then you will see that's going to be 4 pi minus 3 pi over 12. And yeah, we have 1 on our numerator. This will end up becoming, 1 pi over 12, which is exactly what we want. So 3 minus 4 is 1, 1 divided by 12, and you are good to go. So that's what your breakdown is going to be over here. For the pi over 12, we're going to write this as pi over 3 minus pi over 4. And then, of course, go back and use that identity for the negative sign function, right? So the negative sign would be sine of alpha times cosine of beta. So you do start out with the sine, and remember the first angle. So sine of alpha cosine of beta minus cosine alpha sine beta. So using that over here, you will write this guy as sine of, for some reason, it does not like doing like those curved angles. So pi over 3, then you have cosine of the second angle, which will of course become pi over 4. And then keeping the same sign, this will be minus, and then you start out again with reverse, right? So now you will do cosine of alpha, so cosine of pi over 3. And then of course sine of beta, so pi over 4. So go ahead and simplify that, and let me see what your exact value for this guy is coming out to be. So what coordinates will you have for sine of pi over 3 and, well, sine and cosine and pi over 4? So just to show you, pi over 3 and pi over 4, of course, are going to be these two angles over here. So again, just make sure you're sharing your answer only with me, not everyone. And it may not clean up, because you do have some radicals in those coordinates, so you may still have some square roots left over, which is okay. Just as long as you can simplify it, you should be fine. Alrighty, I've got a response from Phoenix here. Very nice, Phoenix. That looks good. Marquise, looks like you actually separated the two answers. Marquise, check that denominator again, please. Okay, if you are having trouble, I will set part of this up for you. So remember, sine of pi over 3 is going to be that angle over here, right? Which means you're looking at these coordinates. So sine would be the second coordinate, cosine, of course, is the first one. So sine of pi over 3 will, of course, come out to be square root of 3, if it will let me write, square root of 3 over 2. Then you're multiplying this with cosine of, wrong direction, pi over 4, which is, of course, the 45-degree angle. So this is where both your sine and cosine have the same values, right? So that's square root of 2 over 2. So this guy will become square root of 2. There we go. That looks like a 2. And then minus in the middle. Cosine of pi over 3 was, of course, again, the 60-degree angle. So that's 1/2. And like I said, sine and cosine at pi over 4 are the same. So this guy is also going to be square root of 2 over 2. So then at this point, you are literally just cleaning up your answer, right? So you will then end up with square root of 3 times square root of 2. 3 times 2 is 6, and that will stay inside the square root symbol, because obviously it doesn't clean up, it doesn't simplify. And the denominator, it's 2 times 2, so that will become a 4. And then minus over here, same thing, we're multiplying 1 times square root of 2 on the top, so that will just become square root of 2. And then denominator is 2 times 2, which becomes 4. Now you can leave that separate, but of course, since it has a common denominator, you can combine them and write it as square root of 6, come on, minus square root of 2. So you actually cannot subtract square root of 6 and square root of 2. Now, if they were inside the same radical symbol, then we could do the subtraction, right? But when they are separate, where you have two separate square roots, you are not able to subtract them. So it will not become square root of 4 over 4, or square root of 4 over 2. So yeah, just be careful about that. And yeah, Marquise, the denominator should be 4. Very good. Exactly. So that's what we should have for this. So this answer honestly is similar to what our 75-degree angle had. And that's okay, because it just depends on what coordinates you had, and the coordinates between pi over 3 and the 30-degree angle basically switch, right? The 1/2 and 1/2 here, square root of 3, square root of 2 over here. So the x and y coordinates basically switch. So it's not really a surprise that this answer came out to be the same as this answer over here. But it's okay. So questions on, of course, first breaking down the pi over 12. So we could come up with those two separate angles, and then just going through the process of using the identity to simplify and find our exact value. Did anybody have any questions on that? Okay. If you don't, we can move forward. So as you can see, we are looking at next example over here. And this one, you can see there's an unknown x value in there, right? So obviously we will not be able to go ahead and evaluate it like we did with example 1 or the try it now number 2, but we can still use the identity to simplify this and rewrite it like they're saying in terms of sine and cosine function. So again, this is a difference identity over here. So you will be doing sine of x, cosine of pi over 4, and then keeping that negative sign here, cosine of x, sine of pi over 4. Now, of course, cosine of pi over 4 and sine of pi over 4, we can again go back and use our unit circle for that. So remember that again is the 45-degree angle. So both sine and cosine have the same value, square root of 2 over 2. So you will see that's where this is coming from. So the sine of x will stay the same. Cosine of x will stay the same, but we rewrite cosine of pi over 4 as square root of 2 over 2. And of course, same thing for sine of pi over 4. You rewrite it as square root of 2 over 2. And they were just asking us to rewrite this in terms of sine and cosine. So, of course, you have sine of x here, cosine of x here. And that's as far as we can go because we don't know what x is, so we cannot simplify it anymore. So they are also saying the identities can be used to simplify the expressions or to try and prove new identities as well, kind of like we did at the beginning of this section to use other identities to prove new ones. So in this one, they're asking us to prove that sine of a plus b divided by sine of a minus b is equal to tangent of a plus tangent of b, and that whole quantity divided by tangent of a minus tangent of b. So basically they're saying choose a side. Which side are you going to begin with, left-hand side or right-hand side? So they're saying since the left-hand side involves those sum and difference identities, we can maybe start with that. So sine of a plus b breaks down into sine of a cosine of b, plus cosine of a sine of b. And then the denominator is the difference identity. So same thing, the only difference is that minus sign, right? But the terms are the same, sine a, cosine b, cosine a, sine b. But now, once we get to this, then, it's kind of like, how do I make this into tangent of a plus tangent of b, or on the denominator, tangent of a minus tangent of b? So it's not seeming very obvious of how to move from there. So maybe instead of the left-hand side, we should start on the right-hand side, and that's where we're kind of going. So let's see how we can break these guys down to help us maybe take the right-hand side and rewrite it so it matches the left-hand side. So let's look at that on the second page here. All right, so tangent of A can, of course, be rewritten as sine over cosine, right? So sine of A over cosine of A. Tangent of B can be written as sine of B over cosine of B. Same thing for the bottom, right? Just with the minus sign in the middle. So sine A cosine A minus sine B over cosine of B. Now, and again, guys, B, just, it's going to take us just a little bit to get through this, but take it step by step over here. So now you can see we have different denominators for, each of these fractions. So that means if I were to find a common denominator, the common denominator would be a product of both cosine of A, cosine of B. So you take that first fraction on the top, multiply it by that least common denominator, take the fractions on the bottom, and same thing, multiply it by the least common denominator. So when you do this, you are going to take this entire cosine of A, cosine of B, and you multiply it with the first term, you multiply it with the second term. Same thing on the denominator. You take that least common denominator, multiply it with the first term, multiply it with the second term. So on that first term, cosine of A here and cosine of A here will cancel out, right? Which means you will be left behind with sine of A from here and cosine of B from here. So you can see that's where sine of A times cosine of B is coming from that first simplification. On the second part where you have cosine of B on the denominator, so when I do cosine of B multiplied with our least common denominator, the cosine of B will cancel out, right? But then sine of B will be left with the cosine of A, because remember, you're doing this twice, once with this fraction, once with this fraction. So there's 2 times that this least common denominator, and this is what I'm calling the least common denominator, is being used. So sine of B gets multiplied with cosine of A, and you can see that's where this term is coming from. Same thing happens on the denominator fractions. When we multiply with the LCD, cosine of A here cancels out. So we're left with sine of A being multiplied with cosine of B. So that's where this fella comes from. On the second term, cosine of B cancels out, which means now we are multiplying sine of B with cosine of A, which is of course where this fella comes from. And those are the identities. You've got sine of A, cosine of B, plus, cosine of A, sine of B, which gives us this guy. On the denominator, you have sine A cosine B minus cosine A sine B, which of course gives us the negative identity. So we started out on the left-hand side and we were like, okay, but when we simplified the left-hand side, we were not able to convert those into tangent functions. So we're like, okay, the left-hand side is not working, so let's move to the right-hand side. And this is essentially what we ended up, but working on the left did not help. So we started out with the right side, break it down, and then once you do your little algebra, magic over there, then we were able to convert it into those identities, and we can say, yeah, it is going to be sine of A plus B divided by sine of A minus B. So remember, guys, there is no clear-cut way of doing this, and there's definitely not a single method or a single process of doing this. You can use different identities, different ways to go about this, and it will take a little bit of practice. This is something new. You've not had to do this before. So just take it easy, take it step by step, and there might be some trial and error involved in trying to get this, simplified, but that's just the way these identities work out. Did anybody have any question on how we broke this guy down and how we came up with that final result? I'm not seeing anything pop up on chat right now. It can be, yeah. Phoenix is saying distributing and simplifying is rough. And, especially when you're dealing with fractions within fractions, that can definitely be, yeah, that can definitely be a little bit difficult because, like I said, there's a lot of math happening in this step just by itself. Setting that up probably will not be hard, but just simplifying it, making sure, we didn't leave anything out or we didn't cancel anything extra that we were not supposed to. So be patient and use, I guess, lots of paper, and you should be fine. Now, you can also use these to solve equations, which is what we did in the previous section, right? We were talking about how we can solve some of these more complex equations. So let's take a look at this guy over here. You have sine of x times sine of 2x, and then you have cosine of x times cosine of 2x, and we're setting it equal to square root of 3 over 2. So basically, you should be able to recognize, and it may take, again, a little practice. I'm not saying you should do this now, but we should be able to recognize that left-hand side actually looks like the cosine identity for the sum, right? The cosine of alpha, sorry, it's plus, so it should be cosine of alpha minus beta. So it should be the difference of angles identity for the cosine function. So your two angles in this case are actually x and 2x. And you can see that's what we have, x and 2x. So this guy you can say is going to be x. This guy is going to be 2x. So that ends up becoming cosine of x minus 2x. And you can see that's what we broke this down into. And then we can simplify that, right? X minus 2x, so that's 1 minus 2, which gives us negative 1. So this ends up becoming cosine of negative 1x, or just negative x, and that's equal to cosine, square root of 3 over 2 from, this right-hand side value over here, which we've just been bringing down with us. Now, same thing, right? Cosine absorbs the negative sign because it's an even function. So the cosine of negative x essentially just becomes cosine of x, and we know the cosine function has a value of square root of 3 over 2 at the angle pi over 6, and the other one is at the angle 11 pi over 6, right? Because you can see this is where we have that positive square root of 3 over 2. So using that, we can say, yeah, you have pi over 6 and 11 pi over 6. They did not tell us that, x is between 0 and that should not be an equal to. they did not give us that caveat here, right? So that means they are leaving it open, and that means you are actually able to use the periodicity of the cosine function, and that's where we bring the 2 pi k into our answer solutions, because we're saying this can be expanded for any value of x, if we use the period of the cosine function. So that's where you come up with these answers from. So, like I said, it may take just a little bit of practice to recognize that, oh, this left-hand side looks like the negative or the difference of angles identity for the cosine function. But once you identify that, you can see it then went pretty smoothly from there onward. So that's what we're hoping to do, when we're trying to solve some of these equations over here. Okay, I thought there was actually a try it now, but I guess there's not one here. Okay. Sorry, again, anybody have questions on that before we move on to that next section with the waves in the sinusoidal graphs or functions? Sorry. Okay. I'm not seeing anything pop up. So this one is talking about combining waves of equal period. So, if you have a sinusoidal function of this form, and remember we had talked about this when we were talking about transformations for the functions here. So they're saying these type of equations can be rewritten using the sum of angles identity. So let's say you have something like f of x is equal to 4 times sine of 3x plus pi over 3, right? So you can see this is where you have two different angle measurements, 3x and pi over 3. So, again, think about this as sine of alpha plus beta, and then you can use that identity. So this will break down into sine of alpha, cosine of beta. We keep the same sign as the angles here. And then this becomes cosine of alpha and sine of beta. So you will see that 4 in the front, because it's being multiplied, will continue, just staying there, kind of like just following along the length of the problem. And then we break this guy down. So sine of alpha, that's the first angle. So sine of 3x, this will be cosine of the second angle. So cosine of pi over 3, and then switch that, cosine of 3x, and then sine of pi over 3, and of course, keeping that same positive sign in the middle. Now, cosine of pi over 3 and sine of pi over 3, we can again use the unit circle and simplify those. So cosine of pi over 3 becomes 1/2. Sine of pi over 3 becomes square root of 3 over 2. So we can go ahead and get those guys cleaned out and then simplify this. So again, remember this 4 will distribute to the first term, and the 4 will distribute to the second term. So on that first term, this 2 will cancel out with the 4 and become a 2. So that's where this guy is coming from. And then, of course, you are keeping sine of 3x as is. And then same thing's happening here because this 4 also gets distributed with the second term. So the 2 over there also cancels out with the 4 and becomes a 2. So then you end up doing 2 times some square root of 3. So, this guys, they will multiply. And then, of course, your cosine of 3x will just come on down. So even if you have something like our sinusoidal function, we are able to use the sum or difference, depending on what it looks like. Mostly it's a plus sign here, but it can be a minus. But yeah, you can go ahead and use the sum of angles identity to try and simplify that down. And again, like we saw with the examples of like cosine of 75 degrees, of sine of pi over 12 degrees, it's kind of just building up on that. Yes, we're dealing in terms of x's and thetas right now, but you will be able to apply this, when we get to applications of how do we break some of those, angles which are unusual and not part of the unit circle. How would you break those guys down? Again, I want to make sure nobody had any questions before I continue forward. So it would be, solving application. So like I said, if you were trying to figure out, what value you would be at, or if you were figuring out, a distance to a place, but you first needed to figure out what the angle is before you could even find the coordinates, because, a lot of times you want to map it, even if it's an imaginary map, we would say, okay, if this is the angle to that location, it could be a ship leaving a harbor and being at a location. And remember, we had done one of those examples, I think it was chapter 1. So, if you were figuring out where the location of the ship is, or we were talking about, with the examples of the London Eye, the Ferris wheel, if you were stuck, let's say the mechanism stopped and you are stuck and they're trying to figure out where you're going to be at. And, it's not always going to be nice, neat, and clean angles, right? So that might be where, now I'm not saying we would be doing those calculations by hand, but even if you're using technology, it's still based on these calculations, right? So a lot of times it could be as simple as figuring out the position of an object, and where or how do we find that? And part of it would be breaking down, with known values so we can find something that's unknown. That's kind of the idea here. Anybody else have a question? Yeah, basically, a means of solving X. Yeah, figuring out what X potentially could be. Very nice. Yeah. So here they're just basically talking about, notice that the stretch to the sine function, added to a different stretch of the cosine function. And they're saying, but essentially both end up having the same horizontal compression, which actually will result in the same period, because, of course, that 3x you can see preserved between both the sine and cosine function. So obviously that value ended up staying the same, but then the 4 you had in the very beginning of the sine function, ends up becoming 2 times the sine function, but then on the cosine side, it ended up becoming 2 times square root of 3. So that's what they're talking about, how the result has a stretch of the sine function added to the stretch of the cosine function. So those are these values up front, but then they're saying the horizontal compression still came out to be the same. So because they both have 3x and 3x, the period of both your sine and cosine functions will end up being similar, because it's the same coordinate, right? The same value. They are also saying this process can be reversed, or they're asking us, can this process be reversed? Can a combination of sine and cosine of the same period be rewritten as a single sinusoidal function? So you can see they're kind of breaking this down over here. And I might need a little bit more time to go over this math to show you how it works in the reverse, because we do kind of have to establish where we come up with these equations from and how we go about doing that, because that's actually the next thing we're going to be doing, is figuring out how we take the uh, sum or difference identity and put it into the single sinusoidal function. So I actually will not be able to complete it. Yeah, Marquise, I did notice that. I'm glad you were able to come back in. So I will stop here, guys. We'll pick up from this next time, because like I said, I don't want to rush through this. We literally have a minute left. So I will stay back. If you have any questions, guys, let me know if you need anything. And if not, I will see you on Monday morning. So be safe, everyone. Enjoy the weekend, and I'll see you on Monday. Bye, guys. Take care.